Welcome. My name is Megan and I am the coordinator for the team. I am accompanied by Adam, our researcher, and Sean, our designer. We are presenting to you our concept for a cost-effective, environmentally friendly alternative for disinfection of water, namely the Watership Down. Before I pass you to our research and design components, I'd like the time to briefly explain to you who we designed the Watership Down for and the community in which it's likely to be used. Sadikola resides within the Gorkha district of Western Nepal. It is a population of approximately 500 people. Villagers working up to and over 14 hours per day and sadly averaging only an income of $240 per year. Sadikola is a hillside community over 1,000 metres above sea level. It receives over 1,000 millimetres of rain per year, but as the end of the dry season in February draws near, water levels in the area decrease to a trickle. Critically, in relation to the efficiency of the Watership Down, the region enjoys 6 to 7 hours of sunlight per day on average throughout the year. Numerous studies have shown that access to clean drinking water is difficult for 1 billion of our global citizens. It is responsible for 2.2 million deaths per year. Staggeringly, in Nepal, 14% of the children under 5 suffer from diarrhea-related diseases, including diarrhea, gastrointestinal problems, and intestinal parasites. In light of the microbial threat from drinking dirty water, residents are forced to collect fuel from the jungle to burn fires and boil the water for disinfection. Not only is this highly labour-intensive, the health risks are increased due to residents having internal cooking spaces with little ventilation. This exposure globally claims 1.5 million lives per year and is proven to cause chronic bronchitis. Specifically for Nepal, 5% of the kids under 5 have acute respiratory infections. Additionally, this collection of fuel is leading to deforestation around the hill communities, with a staggering 2.3% decrease annually in the total area of the Gorkha district's jungle. I will now pass you on to Adam, who will detail the research and justification for our project design.
Industrialised countries typically have major water treatment facilities and supply water to residents via a network of piping. Developing countries such as Nepal, however, typically have decentralised water systems where residents may need to travel distances to source unfiltered water from wells, streams and natural springs. To address water filtration and disinfection requirements, centralised upstream processes must be made affordably available for residents in their home or at the source of water. Point-of-use systems address these requirements and are already found in the homes of developing countries.
Key elements to the success of a point-of-use system in a developing country include initial outlay and ongoing costs. The system must be economically viable. Sustainability. Are the resources required to operate and maintain the system available to the community? Is the system robust and able to provide prolonged service with minimal downtime? And is the community willing to commit to the system's ongoing use? Possible effects on the environment. Are there chemicals required or a byproduct produced that may impact the environment? And to operate the system, does it put added pressure on strained resources such as fuel for cooking or electricity? And finally, is the system appropriate and acceptable to the community? Is extra labour required to operate and maintain the system, given the day for some members of the community is already a labour-intensive day? And will the community understand the concept and accept the need for such a water filtration system? One point-of-view system that meets these key elements is clay pot water filters. The pots are small, easy to use and designed to be used at a household level and will produce sufficient amount of potable water within 24 hours to supply a household, producing approximately 1.5 to 2.5 litres per hour. Economically, clay pots can be purchased at a very affordable price, or if the correct materials are available, communities may be able to make them their own. They work by allowing water to slowly seep through the base of a pot. The mechanism of filtration is determined by the porosity of the medium used to build the filter as variations of pore size alter the process and speed at which filtration can occur. Clay pots impregnated with silver or copper, for example, have shown that the level of contaminant removal is further enhanced. However, other studies have found some filters that do not have metal impregnation applied also removed coliforms equally successfully.
Another point of use system is the use of solar energy for disinfection. Solar disinfection, or SODIS, has been utilised in many developing countries as a point of use system because it is free and easy to source materials. The amount of water that can be disinfected is only limited by the number of plastic bottles available. SODIS is simply achieved by filling PET plastic bottles, shaking to oxygenate the water, and then simply placed under the sun anywhere from 6 hours to 2 days. SODIS utilises ultraviolet radiation, which kills bacteria, viruses and parasites. Warmer water temperature does speed up the process as well.
Another use of solar for disinfecting is solar pasteurisation. Once again, solar pasteurisation is affordable, effective disinfection that is simple to use and offers the ability to build your own. Solar pasteurisation, unlike SODIS, which uses the sun's ultraviolet rays, uses heat from the sun. Pasteurisation is a concept that has been widely accepted for purifying milk and other products, but not so common for water treatment. Typically, a vessel of water is contained within a reflective compartment to maximise heating. Lab results have shown 99% of microbiological contaminants cannot survive in water heated to 65 degrees Celsius for 1 minute. The amount of produced clean water is dependent on vessel size. While some health organisations in the past have encouraged users to boil water to ensure purity, most protozoa and bacteria are inactivated at much lower temperatures. Boiling water is generally recommended to disinfect, but in actual fact it is excessive, particularly for environments where access to fuel is limited.
So if these methods are currently available, why are they not already being utilised? Clay pot filtering is only truly effective with metal impregnation. They can also crack and break, and in order to replace they may have to be sourced from another country. SODIS is time consuming. Communities lose interest due to the long process of cleaning, filling and handling plastic bottles. Bottles are not cleaned sufficiently, the system lacks ownership or pride, and overcast days can increase time required. Solar pasteurisation requires materials not always available. The concept is not completely recognised. The general belief is that water must be boiled to be safe. The systems are not typically robust, and cool weather decreases efficiency. So why combine all three systems? Due to their shortcomings, they are not necessarily reliable or effective individually. Combined under ideal conditions, a combination of three systems provides an extremely efficient filtering and disinfection system. Each system assists in eliminating the deficiencies of the other.
How to combine three systems in one then? All components are contained within a robust manoeuvrable steel container, a 44-gallon drum. Fine mesh provides initial filtering to remove larger particles when filling the first stage. First stage of filtering and disinfection is via a clay pot filter, providing initial fine particle filtering and removal of microbiological contaminants. The second stage of disinfection is provided by clear tubing circled around the drum, providing the benefits of UV disinfection as found with SODIS. The tubing is contained within a reflective back and wings to heat the water inside the tubing to further disinfect, a similar process found in solar pasteurisation. So what are the benefits of our design with the three methods combined? It makes for a robust and suitable design. The 44-gallon drum makes for a sturdy construction and rigid frame, and it helps protect the clay pot from damage. The system is still manoeuvrable to maximise efficiency and is built for the household use, and it provides sufficient potable water for a household, approximately 10 to 12 litres per day. It is technically proven, as all three systems have been subject to significant research separately and have demonstrated their ability to remove microbiological contaminants. Combined, it is economically sound, and as shown, there is minimal to no outlay required for the components. Materials are relatively easy to source. The system is environmentally responsible, as it does not add any extra strain to resources, and no hazardous byproducts are produced. And lastly, it is culturally acceptable. The system encourages ownership, interest and pride, as the system commands significance due to the satisfying level of construction and complexity, and the need for water filtration is already understood, so the system should be welcomed.
Thanks, Adam. My name is Sean and I was a designer for our team, and I will discuss the process of making the prototype and also how it works. During the making of the prototype, I used materials that were available and cheap, although the general design concept is there to see. Instead of a blue plastic barrel, a steel 44-gallon drum will be used. This makes the design stronger and more durable. Clear tubing would be recommended for UV exposure, but the black pipe would enhance the pasteurisation process while drawing in more sunlight, although either type could be used. And obviously a more suitable clay pot water filter would be sourced. In terms of tools and equipment, an angle grinder and jigsaw were used to cut the wings out of the drum, and a drill used to make holes for the cable ties to secure the pipe. Overall, the design was easy to make, and locals in the Sandy Collar community could easily put these together with the right guidance and instructions. Our design is a two-stage system. The first process is that of the clay pot water filter, where the unfiltered water is poured into the clay pot and the filtering process begins. As the water is filtered, it drips into a joining pipe, which is wrapped around the drum, where it is stored and heated to the desired temperature of 65 degrees Celsius or higher to kill the remaining bacteria. To increase the amount of heat generated, wings have been cut into the drum to create a more concentrated heat onto the tubing. The water is then easily obtained from the tap at the end of the pipe, and the whole process is gravity fed, eliminating any need for pumps. Our initial design was a clay pot water filter, but during our research, the group found limitations to the one system. To combat these problems, another system was found. This was a solar pasteurisation process. The group's initial prototype was a clay pot filter joined to a solar pasteurisation hotbox. But while making this, I found it to be a complex task in creating a box to store the system in and also joining the pipes together. To combat this, the drum concept was created, which was a simple and effective design that keeps the clay pot filter protected, and also everything is compact and easy to move around. I may be biased, but I believe that we as a group have designed a reliable and efficient point-of-use water treatment device. Having the two-stage process eliminates any flaws that the other process might have. For example, to an overcast day, the clay pot filter will still be sufficient in providing filtered water. And if there is a problem with the clay pot filter, the solar pasteurisation on its own would also be sufficient in providing clean water. One improvement that could be included is a thermometer, so the community members know when the water has reached the right temperature. This could be built into the tubing or onto the tap. An information pack could also be included. This would include information on how to set up the design and also how to maintain and clean the filtration system. Overall, our design has achieved the target of providing a point-of-use water filtration device for community members of Sandy Collar. It is a simple and low-cost product that would be easily manufactured and produced in the community by the community members. I thank you for your time, and I will now pass back to Megan to wrap it up.
Thanks, Sean. In closing, we feel we have met the requirements for a cost-effective, environmentally and culturally compatible device, one that is very efficient in providing clean water for the villagers of Sandy Collar. On behalf of Adam and Sean, I'd like to thank you for your time and hope that you've enjoyed this presentation.